methods for computational optical imaging.
Thanks a lot. Thanks to the organizers for putting together this event, which has been fascinating and enlightening to me so far. You know, when I was invited, as David Brady, I think, mentioned that maybe he spoke about something different than he thought he may have been invited for. I actually didn't really know why I was invited. So I offered a couple of different topics to the organizers, but I think I also sort of unintentionally manipulated them a bit because I said, well, I've done work in MRI reconstruction with received coil arrays, and that's been successful work. But I'm doing other work that I think is more exciting and original, and so I kind of loaded the question, and Nathan answered, well, of course it's a no-brainer. You should talk about the work that you think is more exciting and original, even if it hasn't been applied in medical imaging in any way yet. So what I'm going to talk about today has not been applied in medical imaging in any way yet, but I hope that there's some interesting take-home messages for you, and there's a whole day and a half of conversation left to talk about how one could build on some of the things that we've done. So my talk has just a single simple thesis. It's that in imaging with light, the spatial resolution can be derived from time resolution. And by that I mean it can be derived computationally when you have time-varying illumination and time-resolved sensing. So I'm going to concentrate on just one problem that we solve using this space-from-time imaging idea, and that's the formation of depth maps, or a new technology for formation of depth maps. I hope that that one example convinces you that the basic idea is actually pretty simple, practical, and worthy of further analysis and development. In such a short talk, I'm not going to talk about a variety of different technologies, and actually I realized that I think my talk is going to be quite different than most of the talks thus far, because I'm going to just tell you in detail about one thing we've achieved rather than to give an overview of an area. But the main precedent for our work, you'll see, is third-generation LiDAR, or what's called full waveform LiDAR, but it's also quite distinct from third-generation LiDAR. So if you know what third-generation LiDAR is, it's LiDAR in which you don't just get a single scalar distance measurement, but instead you try to process an entire received waveform. But in third-generation LiDAR, using that entire received waveform, you're still only trying to get improved longitudinal information from having that full waveform. What we're doing is rather different than that. We're trying to actually get transverse spatial resolution from time-resolved sensing, and I hope that I'll make that clear today. So what we're doing involves high-speed sensing. High-speed sensing is usually associated with stopping time. Actually, Stopping Time was the name of a book of photographs by Harold Edgerton. It collected photos that Edgerton produced from the 1930s to the 1970s. What we're doing is not trying to stop time, but instead use time-resolved photometry along with computation to make interesting inferences. So, another early example of stopping time was that Edward Muybridge, I think in 1872, settled a bet for Leland Stanford. He settled the bet on whether a trotting horse has all four of its feet off the ground at the same time. The answer is yes, and I think that's the side of the bet that Leland Stanford was on, but I'm not sure if that affected how Muybridge was paid. In these examples of stopping time by having high-resolution, high-speed sensing, the spatial resolution is still entirely from optics. The spatial resolution is certainly not computational because these methods really had no computational aspect to them. And what we're going to do is we're going to create time variations in the scene by having time-varying illumination, and then we're going to have sensing that's fast enough to capture those time variations and to make inferences from it. So it's not just stopping time, but we need to have time-resolved photometry and interesting modeling and computation to be able to make our inferences. So I'll introduce you to the ideas of space-from-time imaging through two examples. First is what we call diffuse imaging, which is not really related to the last talk, and maybe we should have a different language, but we call this diffuse imaging. We call it diffuse imaging because the illumination is spatially diffuse and the sensing is spatially diffuse. And the goal is to form essentially an ordinary image, like a photographic image of a reflectance of a scene. I'm going to talk about that very briefly because I think it's actually relatively simple and straightforward. I'll spend more time talking about what we call compressive depth acquisition, and there we're trying to form not ordinary images but depth maps, so an array of numbers, but the numbers now don't represent reflectances, they instead represent distances between the imaging device and the scene. So when I go through these examples, I think you may have the reaction that, oh, it's all just signals and systems. And I don't take that as an insult at all. I think it's fine if you just take this whole talk as an advertisement for the power of signals and systems thinking applied to optical intensity signals, which is not the usual way that we think about optical imaging. So that may be one of the major take-home points from the talk, actually. Now, the first example, again, that I'm going to talk about very briefly because I want to stay within the time and allow some conversation, is analogous to conventional sampling theory and is therefore rather simple. The second example, where we try to form depth maps, we use some parametric sampling theory to get the results that I'll show you. So let's first suppose that we're trying to form an ordinary photograph. So the normal way to do this would be to have the light reflected from the scene focused onto a measurement plane. Here I've just drawn one lens, not a compound lens, but you get the idea. So the normal way would be to focus the light back onto a measurement plane, and the spatial resolution you get is from that focus and from having an array of sensors at the measurement plane. And that spatial resolution on the measurement plane maps back to the spatial resolution on the scene. So that's a very ordinary way of forming images. Now, something far less common, but conceptually valuable, especially when we move to depth map formation, is literally the Helmholtz reciprocal dual of ordinary photography. It's called dual photography. And what we can do instead is to have a spatially addressable light source that really focuses light on one scene patch at a time. Then the light reflected back from the scene can be collected at a single photodetector, and we call this dual photography. So in either of these, the ordinary photography or the dual photography, all of the spatial resolution is coming from optical focus. Now, what if we try to form images without that kind of optical focus at all? So we have an omnidirectional source of light. I'm going to consider it to be an impulse in time for convenience. The light will spread as it propagates. It'll hit some parts of the scene first. It'll hit other parts of the scene later. The light, I'm going to assume, reflects that the surface is a Lambertian reflector for now. So the light is going to reflect diffusely from the scene. The light leaves some parts of the scene earlier than others because it reached the scene, some parts of the scene earlier than others. And it spreads as it propagates, and it could reach some detector plane where we detect with fine resolution. Now, this way of looking at optical measurement really treats our process as measuring impulse responses. There's an impulse response that can be measured at a detector point D1. There's an impulse response that can be measured at this detector position D2. Those impulse responses have embedded within them the reflectance of the scene in a somewhat complicated, but really not that complicated way. It just involves integrals over ellipses. So it's not that complicated, and I'm omitting that, any further discussion of that. But the information we care about is embedded in what we can measure in a linear way. The information that we can collect at one scene location is not enough to actually form an image of the scene, but if we had detectors at a set of locations, then collectively we can end up with a one-to-one mapping, and we can invert that. So I'm not going to delve into this further, but I think maybe many of you can imagine that it's pretty simple to put together to write out the details of a linear forward model. And then this is essentially like a Hilbert space sampling theory. It just is a Hilbert space sampling theory that doesn't have shift invariant basis functions, but it's really not that more complicated than a basic sampling theory. A small amount of spatial diversity in the source detector pairs is what allows us to form images here. And you can imagine using this in direct configurations or non-line of sight configurations where bouncing light off of a Lambertian surface becomes a virtual source of omnidirectional illumination. And that's something that we've actually experimentally verified. But what I'm going to spend most of my time on today is recovering geometry. And if we try to just formulate this in a completely straightforward manner as I've just described, then the parameters of interest, these geometric parameters, affect our measurements nonlinearly. So we could write down a forward model, but it would become a nonlinear inverse problem. And we need to do something a little bit more clever to have something that we can robustly solve. And that's what I'm going to get into. So I'll describe a signal processing framework that we introduce that leverages parametric sampling theory applied to one-dimensional functions, and I'll describe a couple of experimental verifications of our framework. So we want to do depth acquisition, and there are a lot of technologies that exist for depth acquisition. Oops. Something funny is going on. Okay, so there are stereo camera techniques to form depth maps. Of course, stereo cameras have multiple lens and image planes operating in parallel. They're usually used just to simulate human binocular vision, but you can also do some post-processing on that data using correspondences between what you see from the different lens systems to form depth maps. These methods can work fine, but the main difficulty is that inherently the depth resolution must become worse as you get further from the imaging device because, of course, the scene points don't look so different as you get further from the two systems further from the imaging device. A Kinect is a very widely deployed technology now for depth map acquisition. It has some of the same weaknesses, actually, of a stereo camera system. In particular, the depth resolution of a Kinect also becomes significantly worse further from the imaging device. And a Kinect is not at all robust to ambient light, so you can't use a Kinect in direct sunlight. So the kinds of methods that overcome those two fundamental difficulties, that is sensitivity to ambient light and having poor depth resolution further from the imaging device, are the ones based on time of flight. So a LiDAR system is one that literally raster scans the scene with the illumination source. So you use a directed light pulse, but you raster scan and therefore have a time to collect the data that's proportional to the number of pixels, or you can try to make all those measurements in parallel by having an array of sensors, and that's what a time-of-flight camera does. So a time-of-flight camera will illuminate an entire scene with a time-varying illumination, will focus the reflected light back on an array of sensors, and each element of the array will, in essence, give one distance measurement. There, the cost of the system will end up being proportional to the number of pixels, and those array elements have non-trivial cost. They're not like CMOS sensors that are used for RGB imaging that might cost microdollars per pixel. These have significant cost, and so $5,000 depth camera might have only about 300 by 400 spatial resolution. Okay, so what we're after, and what I'm going to describe today, is a way to do depth acquisition with just a single photo detector and without raster scanning of the scene by our light source. So first I want to explain in a little bit more detail how a conventional time-of-flight camera works, and then we'll see the difficulties that arise when we go from having an array of sensors down to a single photo detector. So a conventional time-of-flight camera is going to illuminate the entire scene spatially with a time-varying illumination intensity, S of t. Light will be reflected back from the scene, and there's optical focus in that reflected light, focusing that reflected light onto an array, so that there's a one-to-one correspondence between scene points and array elements. So essentially there's separate problems to solve for each array element, and at each array element you essentially just want to know a phase offset or a time delay between the transmitted light and the received light. Here I've written it as a cosine just because phase offsets are rather intuitive, but these are intensity signals, so they're all non-negative signals. So it's very simple. The computation is kind of trivial per pixel. We want to get away with having just a single photodetector. So we need to do something to get our transverse spatial resolution. If I was going to illuminate the entire scene and just have one photodetector, I would get no spatial resolution. We get our spatial resolution fundamentally because we introduce a spatial light modulator. So we have an intensity modulated light source, but also a spatial light modulator. So our illumination of the scene is really an illumination of a pseudo-random subset of the scene because the spatial light modulator has a binary pattern on it. So we illuminate a subset of the scene. The light is all reflected back and focused on a single photodetector, so it's an integration over space. The photodetector produces an electrical output signal that's sampled in time and value, and we repeat this for several different pseudo-random patterns on this SLM, and then with some nice signal processing, we're able to form depth maps. Now, this might look familiar to some of you. It may look a lot like a compressive architecture for imaging. So I want to show you why we can't apply vanilla compressed sensing techniques here, and then what we had to introduce or what we came up with as alternative to vanilla compressed sensing techniques. So let's suppose for a moment that we had the device exactly as I described, and we were trying to take photographs rather than form depth maps. Then our problem would be relatively simple because the measurements would be linear combinations of what we care about. So let's say that each scene point has a reflectance that's represented with an x. So xa is the reflectance of scene point A, xb is the reflectance of scene point B. Then if I illuminated the scene and measured as I described, and integrated over time, I would essentially get a linear combination of the reflectances of A and B. In compressed sensing, that's what you essentially want. You want to measure a bunch of linear combinations of the quantities that you care about. But we don't care about the reflectances, we care about these distances. So taking a very simple example of illuminating only two scene points, let's look at what happens. Well, when we illuminate just two scene points A and B, and we get reflected signals from those scene points, we'll get a signal from which we could estimate an amplitude and a phase. If we knew the reflectances XA and XB, we could solve for DA and DB, the two distances that we care about, but it's nonlinear, it's messy, and it's not something that would scale well to illuminating half of the scene points at a time when the number of scene points is 1 million. So this is not the way we would want to approach the problem, and we can't really treat this as a vanilla compressed sensing problem. So one key to what we're going to do is that we're willing to model the world as well approximated as piecewise planar. That works for interior scenes. A lot of times the capturing of depth maps is for things like teleconferencing, where you want to establish the geometry of a room. So it can be useful for those kind of interior geometries. It's good for exteriors of many buildings, including relatively crazy views of some Frank Gehry buildings. It's not necessarily going to work for every view of every Frank Gehry building. Okay, so what I'm describing today is limited in a way. It's limited to forming piecewise planar models of the world, or at least the way I'm explaining it is limited in that way, even if our experimental results make me optimistic about going beyond that. So now for even greater simplicity, I'm going to explain the principles, assuming that not only is my scene piecewise planar, but that the planar facets are frontoparallel. So in that case, the light that's reflected back from the scene has a parametric form. And we'll denote that parametric form by P of t. Embedded in that function P of t are quantities of interest, for example, these depths d1, d2, and d3. We'll have the photodetector that we'll use and the whole sensing system that we use will be relatively cheap, so it'll have an impulse response that is not very narrow. Also, if since everything here is linear and time invariant, if the illumination is not an impulse in time, then the illumination waveform can also be incorporated into this H. But what we're able to measure are discrete time samples of the convolution between this parametric function P that has embedded in it information that we care about, and this much fatter function H of t. But because we have a parametric model for this P of t, we can use parametric deconvolution techniques or parametric sampling techniques to get a very accurate estimate of P of t. Now, this doesn't give us any spatial resolution. To get spatial, the transverse resolution, we are illuminating a subset of the scene at a time. The result of illuminating a subset of the scene at the time is a response that is below the envelope of the blue signal. And the relative heights here give us information. So the relative height of this first blue pulse red pulse relative to that blue envelope tells us the fraction of the scene at the depth d1 that's illuminated with this particular pattern. And so we've done two things here. One, we've introduced parametric modeling of P of t so that we get very high depth resolution relative to the speed of the sensor. And the other thing is that we've come up with a way to interpret the red signal that makes our measurement be inner products between quantities that we care about and quantities that we can measure. So in a way, we've linearized our problem. We've linearized the forward model by introducing new variables. So we introduce variables that are binary variables that we call depth masks that represent, that have ones in the spatial positions where a particular depth is present. And then the measurements that we make are effectively inner products between the binary pattern on the SLM and those new variables, those depth masks. We can gather all the data over several different binary patterns on the SLM, and now we have a linear forward model but with new variables. I won't get into the details of how we now invert. We put together an optimization formulation to then solve for these new variables, these depth masks. And where we have binary variables, we use a convex relaxation, and now we have a simple optimization problem to solve that gives us the depth maps that we're after. So there's a two-step acquisition process, as I've described. There's a first step where we get the depths that are present in the scene, and then a second step where we get all the transverse spatial resolution. And we've experimentally verified this. In a scene where, yeah?
Rate limiting step, is it actual data acquisition or is it analysis?
Well, we've not attempted to make the computations real time, really. The acquisition can be very fast because changing the state on an SLM can be done very fast, whether it's a piezoelectric phase-based SLM or whether it's a digital micromirror device. Either way, you can change the state pretty fast. So certainly in our system so far, we're computation limited, but we haven't really pushed that.
Right, and thank you. And the reason I'm asking is you could think as you move forward in time, in
Yeah.
your research, to wanting to look at more realistic structures and then the dynamics of them. And so you need to be able to do the whole thing, that is the data acquisition analysis, on a time scale where the structures that we were dealing with are stable, that is not changing during that process. So,
right,
yeah.
right, I agree. So in the case, in our experiment where we have frontoparallel facets, everything works exactly as I described. But the same kind of thing works without frontoparallel facets. So again, to look at the results from this experiment, we get these depth maps that are 64 by 64, so they have 4,096 pixels. We achieve that using 205 patterns on the spatial light modulator, so that's like a 20 times speed up over a LiDAR system. More interesting probably is the depth resolution that we achieve. So we use a simple silicon pin diode with a rise time of 0.7 nanoseconds. And when you multiply 0.7 nanoseconds times the speed of light, you get 21 centimeters. That's telling you that information from a slab, a longitudinal slab of 10.5 centimeters is all smeared together within the rise time of the sensor, and yet we get clearly sub-centimeter depth resolution. All of this can be made cheap, but that's probably not what's of primary interest in moving towards medical applications. Spatial light modulators can be cheap and can change state very fast. We're already using extremely cheap detectors. And an alternative configuration that we've also experimentally verified is one where all of the spatial patterning is done not with how we illuminate the scene, but with how we capture the light, because the light is focused onto a digital micromirror device, and then that has certain on pixels and off pixels that directs the light to an avalanche photodiode. So this compressive depth acquisition architecture, we think, is the first mechanism that allows you to capture depth maps with a single time-resolved photodetector without raster scanning a scene as in LiDAR. So backing up now and wrapping up the talk, space from time imaging is a set of techniques for providing spatial resolution from computational processing of time-resolved samples of light intensity. I just went through in some detail one particular example where we formed depth maps in a perhaps cheaper way than depth maps are usually formed. We're obviously using the finiteness of the speed of light here, but we're not using it just to form scalar distance measurements, but instead to capture these intensities as a function of time and to make further computations from those full waveforms. There are a lot more things in this line of work from my group, but in particular, I want to point out that everything I described is based only on simple facts from geometrical optics, rather than incorporating any of the aspects of Fourier optics here. We're also working on explicitly using Poisson process models for the photon counts at very low signal strengths, and we think this will give us ways to form depth maps and very high photon efficiency. And there also definitely are methods, there are relationships to methods at other EM wavelengths. So there are relationships between what I've described here and, for example, synthetic aperture radar. So there are several papers that I can refer you to. I won't comment on these, I'll leave this on the screen, but I'll just wrap up by telling you what I think should be the one takeaway point that you might apply to your own work, or that we might together talk about how to incorporate it into other systems. What we've achieved here is this very high depth resolution relative to the speed of the sensors. You can ask why. The fundamental answer to why we're able to achieve that is that we use parametric modeling and parametric sampling theory. And I think that one aspect is something that may well be incorporated into various different modalities. And that's what I really encourage you to do, to look at whether those parametric modeling ideas can be incorporated into the modality that you're interested in. I'll stop there. Thanks.
We've got lots of questions. Speakers first. There we go.
In your model, as far as I understand, you ignore the coupling between objects. So in your model, forward model, you're ignoring, as far as I can understand, the coupling between objects and non-objects in the scene. What would happen if you were to have that realistic model where objects could act as secondary sources for other objects?
Reflections and
multiple
scatter.
interreflections. Yeah, right, okay. So actually, that's something we're working on. I mean, so to be really picky, okay, so I'll point out something which, I normally wouldn't point out, but there's an interesting slight bias in this. I didn't try to show you the accuracy of this depth map. It's actually giving slightly greater depth at the center there than the true depth. And I think that bias is actually due to interreflection, and we've been working on models that include interreflection that would remove that tiny bias that you can barely see, that you can barely eyeball there. But we're definitely working on more complicated interreflection models.
Okay, did you have a question?
For these results here, was the actual grid that you did the solution on different than this grid? Was it a denser grid, or was it actually what you were showing here?
Oh, it's this grid. So 64 by 64 is the resolution at which we addressed the SLM, and then we reconstructed at the same spatial resolution.
Yes.
I was just curious, how much does this depend on having a homogeneous refractive index of the medium surrounding the object?
Yeah, so I guess the properly cautious answer is that it depends a lot on that, and I can't really say anything about a medium with variable refractive index.
That's most biological samples.
Yeah, no, I agree. Yeah, this is kind of a pure reflection mode experiment with this free space propagation up until you get to the reflective object. So I think it's certainly possible to extend the models, but it would increase the number of unknowns in the models considerably, and that's not something we've explored in any detail yet.
Work to be done.
Work to be done.
Yeah, that's right. Early days.
Great. There is an analogy in ultrasound that you do. We have been working on what we call time reversal kaleidoskop. It's a way to, instead of using 2D arrays, transducers in order to do 3D images, we use only one transducer, but instead of having all this spatial complexity of 2D arrays, we put all the complexity in time signals.
Okay.
And to do this, what we do is we have only one transmitter, but we put just in front of this transmitter a kaleidoscope, a medium which is reflecting in all directions of the beams. And here you've got the same kind of concepts. We create a noise, and we are going to use this noise to put the spatial complexity into time complexity.
And that object that modulates the transmitter, that's then varied in some way too?
Yeah.
Okay.
And the question is, in our case, in order to be able to find the two transmitted signal, to focus everywhere we want inside the medium, we have to use time reversal. And time reversal, I think time reversal is hidden in what we do. Time reversal is a match filter, and when you do your inversion process, you do a match filtering of the Mills function between each pixel of the SLM with the other ones. And I was wondering if you tried already to do this kind of connections with time reversal.
We didn't try that, but I think I understand what you're saying, and I think it is something we could attempt to verify experimentally also. Yeah.
Can you apply time reversal in this case because you don't have the phase information? In your case, I think you have the advantage of working with acoustic signals, and that's why you have a fantastic complex signal that you can do whatever you like. But here it's more difficult.
But with the settings, you can determine those things because as you change your...
But the detection is abnormal, your detection is complex. That's where you rely on computation and the model to have a simple form model to recover what you've lost.
Right. Oh, you're saying it's only possible with coherent detection to even imagine.
Yes, some sort of phase recovery.
Yeah.
So what if one chose to do different transverse modes and not use of the light? Do you think there would be something there?
But for a linearized problem, the adjoint of the forward operator is the fully spatially variant match filter at every point you've seen. So if you were not using an adjoint or within the iterative process, how was your iterative system solver finding a solution? Did you use explicit matrices for your forward operator?
Yeah, so we explicitly form these matrices, but then we just drop it into CVX.
Okay.
So, at least for this, for this piece of research, we've not bothered to look under the hood in terms of exactly how to solve this convex optimization problem. Yeah, and these operators, well, actually, oops, it would work if I do that. This is the matrices here are just the SLM patterns. There's nothing more in there. The propagation effects have already, I guess, obviously a lot of details are not in this level of talk, but the propagation effects have already been, in some sense, removed when we do this, when we deconvolve and get these p-hat signals. Yes, please.
One more. I'm thinking about this too. I'm supposed to be chairing.
The new pattern, what we have seen is that we are able to increase a lot the resolution of the system because at the end, the aperture is not the transmitter or the receiver. The aperture is the medium itself because you've got multiple scattering everywhere. And here, perhaps you have the same kind of ideas if you are able to reflect your light beams on these several objects that are separated in space. You could reach a resolution which is better than a medium in free space.
Okay, no, look, I mean, it's just great. That's why we're supposed to be here. But we also got some practical realities. And so I think, fortunately, we're all going to be at this dinner. Because I'm interested in thinking about the transverse polarization too, which has phase information. So, and there's polarization, and then there's polarization we haven't even talked about. But see, that's the problem with good talks, with good ideas. Gets us going too much, and we have another excellent talk about it again. So let's thank Vivek again.